Wow, some of these jokes are really bad. I just thought I'd mention that. We'll get started soon. Hello, everybody. There we go. I had the headset muted there. See, that's a much better chemistry joke. Did you know that oxygen and magnesium were getting engaged? OMG, I didn't know that. Yeah, I guess that my jokes aren't that much better, so that's okay. We're gonna get started here. Oh, I left my little test drawing up there to make sure that my pen worked. But we're gonna start here. Yeah, I know. Now people are gonna come in and hear my terrible jokes too. I think by default, chemistry jokes are required to be awful. Like, that's kind of the point. I mean, if you can tell me a good chemistry joke that's, like, not just, like, super niche and, yeah, that sort of thing. Anyway. So, today we're going to start talking about precision and accuracy in measurements. If you were in the laboratory and actually were making measurements, you would be doing them multiple times. Now, depending on the nature of the experiment, you're going to have long experiments in which you're going to do like 3 or 4 trials, or you might have really short experiments where you could do hundreds of trials. Physics is notorious for this because you can do an experiment where like you drop a ball and you try and measure how high up it bounces, and that takes like a second. So you can do hundreds of trials and get a really good statistical average. In chemistry, if you do 100 titrations, you might be there all day. So it's important to realize that we are using precision and accuracy as a means of doing statistics, but in chemistry, we're going to do it kind of fast and loose here. And we're just going to make a sort of assumption based on how close the numbers look, instead of applying something like a standard deviation or figuring out an uncertainty or stuff like that. So, taking measurements repeatedly and then using the average result is good practice. For the most part, we're going to do 3 or so trials, which statistically isn't significant if you have a lot of error. But that's okay. That's just all we really have time for in the laboratory. Now, of course, the reason that we want to do that is because most error can be averaged away. If you have random errors, for example, maybe the balance is reading too high one time and then it was too low the next time, you can average those out. Some types of error can't be averaged out, though. If you don't hit tare every time, you're going to have an answer that's too high or too low, depending on what error you made. So we're going to talk about those types of mistakes that can be made today. We're going to categorize them as different types of error. And then we're going to talk about their impact on your results, because some of that will be useful in your laboratory worksheet that you're going to be working on this coming week. All right, so for instance, on the board here, I have a bunch of data. This is data collected from the volumes of medicine dispensed by a 10-ounce dispensary. So presumably the device would be calibrated at some point to dispense 296 milliliters of medicine. And so that's what's indicated right here. But over time, things happen to these machines, like they get off calibration, or maybe something is screwed up in it and it's not dispensing correctly, like the flow nozzle is plugged or something. Or maybe like the container in which it holds the calibrated sample got expanded or something due to heat or whatever. And the numbers are going to change. So we have 3 different dispensers here. And what we want to try and consider is, what is making these answers wrong? Like, what feature about them can be reflected in something that could be wrong with the machine? So, for instance, in dispenser number 1 here, we could look at all of the numbers that are generated and then compare it to the correct answer. And if you're looking at those numbers and saying, wow, those aren't really close at all, this machine is way under dispensing, then you're right. But what else could we say? We could say, well, hey, those numbers are fairly close together. It's getting a roughly similar amount every time. So is the machine just miscalibrated, or is there something wrong with it and is just dispensing a seemingly random amount? And we can make a conclusion from there. So the first conclusion that we're going to make is that if we have all the data that's really close together, so these numbers, again, are fairly close together, we're going to call that precise. Data is precise when there's little deviation between each of the values. When I say little deviation, I mean like plus or minus 1 to 5% or so is typically acceptable as precise. Here you could just tell by looking at the numbers, oh, they're all within 1. So yeah, that's pretty precise. What about dataset 2? Dataset 2 is pretty close to the target, but there's a lot more deviation in those answers. So what we can say here is, because these answers for dispenser 2 are much closer to the target answer, on average anyway, but the variation is between 5 milliliters or so, because we can range all the way from 293 past 298. That's a big window. That's plus or minus like 3 in each direction. That's not very precise. However, it is what we would say is accurate. Something is accurate if your average is close to the correct average. When we say the correct average, what we really mean is what we have accepted to be as correct. So, for instance, if I said, like, what's the true density of aluminum? Well, thousands upon thousands of experiments have been done to determine this number, and we've basically taken the average over all of them, and that average is the true value. Now, is it exactly right? No, it's not a definition. It's just something that we have measured, and using the tools that we have available, this is the closest answer that we've gotten so far. Now, is it possible to be both precise and accurate? It turns out, yeah, it's totally possible. Over here on number 3, you'll notice that not only is the data average really close to the target number, 296, but the deviation is less than like 0.2. So dispenser number 3 is both precise and accurate. Dispenser number 1 is only precise, and dispenser number 2 is only accurate. It is possible to be neither precise nor accurate, and that's basically would be a dispenser that was just spitting out random numbers, like 38, 306, 150. Like, those aren't precise or accurate at all. That's just essentially random. And we've already done this, so there we go. There's your answers for these 3 sets. On a assessment, you may be asked to look at some data and tell me, hey, is this precise, accurate, both, or neither? With precision, again, just look for numbers that are relatively close together. If the last digit or the last 2 digits are close enough, so these digits right here, I would say. What I've underlined, those numbers are all totally random. It's basically, the range is very large, so I would say that that's not precise. But over here, these are all more or less the same, so I would say that those are precise. And I will try and make it as obvious as I can. Now, when you are doing an experiment, or doing any sort of activity in science, really, there are many ways to do a task, and almost all of them are wrong. Usually, there is one very specific way that we will want you to go about accomplishing some sort of need or necessity or whatever. For example, reading a cylinder and measuring its volume requires a very specific technique, and you might not be aware of that. In fact, most people might assume, oh, I just look at it and read the number, and it turns out that if you do that based on how water behaves, then you'll get an error. So if you look at this curved thing right here, oops, that wasn't very good, hold on. Boop, try again. So if you look at this curved thing right here, that wasn't much better, but it's better enough. What this is called a meniscus. And the reason that water does this is because water likes to engage with other substances that also contain oxygen. The hydrogen part of water actually will stick or be attracted to other substances that have oxygen in it. This is called hydrogen bonding. This is something we're going to study at the very end of Chapter 4 as actually part of Chapter 10. We do cover it in this class, and it's very, very important for Biology 211. But this property of water allows it to stick to the sides and be attracted to it, which means that the water tries to climb up the sides of the glass container. In the center of that, which would be kind of like, I guess you could think of like a trampoline with a heavy object in the middle. In the very center of that is the lowest point of the water meniscus. And that's the point that we measure the volume from. We've just defined volume to be measured from that spot. Now, in order to find that lowest point, that requires you to look at your meniscus head on. And if you look at it from any other angle, then what ends up happening is that where you see the meniscus ends up being on a different mark than where it actually is. And that can actually provide a lot of error. This graduated cylinder is not actually a graduated cylinder, it's a burette. So burettes actually measure from top to bottom. So 0 would be up here, and then 50 would be at the bottom. But you're right, yeah, that does look very strange if you didn't realize what a burette was. A burette will be discussed in more detail in the lab worksheet that I posted. But think of a burette as something that measures how much liquid is dispensed and not how much it holds. For example, if I started here on my burette and then I ended here, then I dispensed the difference. And that stuff would be in my little container at the bottom. Alright. Now, depending on how you read this scale, you may make a mistake and get a wrong result in either direction. So if you read it too high, your number is going to be too small on this scale. If you read it too low, your number is going to be too large on this scale. And the places that these numbers are being read is right where the eye meets the glass. So right here is where this guy is reading it, which is why he got a number that was too large. And right here is where this guy is reading it, which is why he got a number that was too small. Now, presumably, you would do this either the same wrong way every time, or perhaps you would do it randomly the wrong way every time. Maybe you'd hold it above your head, and then you'd hold it below your head, or whatever. Depending on what you do, that's going to be a different type of error. So the first type of error is called systematic error. Systematic errors are errors that are the fault of how you are doing the experiment. For instance, if I always look at my meniscus from above, I will get an answer that's too small, and my answer will therefore be too small. If the answer was, how much volume did you dispense, for example. Now, systematic errors affect the accuracy of your data, but because you're doing the same mistake every time, you could still have precise work. Systematic errors, generally speaking, don't affect your precision as long as you're only making one systematic error. Now, if you were in the laboratory, I would be saying something very different. I would say, hey, you're new, you're going to make errors all over the place. We're going to just work on precision and hope for the best. And if you get somewhere close to the right answer, that's good enough. Now, it's possible for you to just make a mistake because you are doing the experiment just completely wrong, and you have no idea what you're doing, so you're not following any sort of system at all. However, you could also make errors by doing the experiment perfectly right, and then those errors come from outside sources. These type of errors are called random error. Random errors are random, as the meme would suggest, and they can come from anywhere. For instance, if you are working in a laboratory where you are using water and measuring its properties, and then the heater kicks on, and the room slowly heats up, the water will expand, and its volume will slowly change. Then maybe the heater will turn off, and then the room will cool back down, and the volume will slowly contract. All of those results could affect your outcome. Maybe you're trying to read something and your hands are shaking, but they're shaking in such a way that you just get a random offset for the number that you're trying to read, or whatever. Or maybe there's air currents flowing over the balance, or all sorts of different things. The way that you can get rid of these errors is you just average your results out. If random errors are truly random, then half of the errors will be too high, and the other half will be too low. And when you take the average, you should mitigate the source of the error. So random errors will generally affect precision, and this can also affect your accuracy, especially in our case when we have too few trials. So let's indicate that. So too few trials. If you had tons and tons and tons of trials, the effect on accuracy would be really minimal. In our case, random error can affect accuracy just because our sample size is too small. On the screen here, I have a picture of 4 bullseye targets with 4 people who went to the range to, I don't know, practice marksmanship or whatever. On the top here is just somebody just randomly hitting the target. Now, it's actually impressive if you do hit the target. But if your target was to get the bullseye right here, and these were the data points that you provided, those are not accurate or precise. If I wanted to take the average, what I would do is something like this. I'd say like the average is like right there. That's not very good. Over here is what we call statistics. Statistics. There we go. Because if I take the average again like I was doing before, that's actually much better. This is known as the Statisticians Bullseye. If you shoot a deer 20 feet to the left and miss, and then shoot the deer 20 feet to the right and miss, the average will hit the deer square in the head, and you will get a kill. That is not how it works, but that's how statistics should work. Over here on the bottom left target here, we have somebody who knows what they're doing. In fact, you can tell this because all of their shots are clustered very close together. Now, there is some sort of error here. This is endemic of a systematic error. And the systematic error here would be something like, oh, this person is aiming at the target, but their weapon isn't sighted properly. Like, it's just a little bit too high and to the left. So that could be something that could be easily remedied. And then over here, this is my Shadowrun character. He is a marksman, and he hits the bullseye every time. That's what happens when you throw 15 dice. You just hit things. As you can see, the average is very close to the bullseye. It might just be the bullseye. Now, the 4 shots aren't exactly the same because there is going to always be some amount of random error. And that could be things like wind or shaking hands or something like that. No matter how steady your hands are, the slightest fluctuation can change your outcome. All right, so that's a discussion of precision and accuracy and sources of error. Um, if we were in the laboratory, I would be asking you to cite these sources of error. I'd say, what did you do to create this error? And then tell me whether it's systematic or random, and then tell me how you know, basically. Like, can you go back and say that? And that would be something like, okay, well, this was the outcome. If I could get my cursor to stay on the screen here. Okay, if this was my outcome right here, then this is what happened, and this must be the reason. That's the sort of logic that I want you to follow when trying to assess error in chemistry. And again, how do you know what's systematic and what's random? Well, we just went over the different ways that these errors are shown. Systematic errors generally affect accuracy, and random errors generally affect precision. Now again, because we take so few data points, this one can also affect accuracy as well. But as a general rule, if we took 1,000 data points, it should only affect precision. All right. And so there's our discussion right there. So remember that you can take random error and average them away, which is why we do more trials. Systematic errors. Oops, my chair just fell backwards. Hold on. Systematic errors cannot be averaged away because you're making the same mistake every time. And that's pretty much all there is to error analysis. So this slide is just basically saying that, hey, we want to be precise and accurate. It is my preference for my students that when they are beginning that we focus on this one, because precision implies that you have better lab technique than you started. If you just go in and spin knobs and pour things into other things, you're going to get a random answer, so you're not going to be precise. Having some level of skill indicates that you are working towards becoming a precise chemist, and that's really the goal of the general chemistry series, is to get you to get reproducible outcomes so that you know what's going on. I think that's it. Yeah, it is. Okay, cool. All right, so if there aren't any questions, I'll give you a few seconds to compose your thoughts. The next section that we're going to be doing is math. Dun, dun, dun. Everyone's favorite section. We're going to do dimensional analysis. I'm going to show you how I want you to do dimensional analysis, and then because this is an online class, you can do whatever the hell you want to, because I can't stop you. But for future classes, it will be very important that we follow unit cancellation rules, and you show your work in a very clear and concise way. And we'll talk about what that means in just a second. But yeah, if anyone has any questions, I'm going to go fill my water, and then we'll get started in about a minute. There we go. Yes, it's everyone's favorite. Everyone loves dimensional analysis. Hooray. As a scientist, dimensional analysis never goes away. This is something that you will basically do forever. And depending on the context of your job, the outcome of doing dimensional analysis may be as important as administering the correct amount of medication to a patient, or making sure your space shuttle doesn't crash land on Mars because you used imperial units instead of metric ones. True story, that has happened. We're going to be doing a lot of work in this class in the metric system. However, because we live in America, the imperial system is a thing. We're going to learn how to go back and forth between both of those. But most importantly, I'm going to show you a reliable, reproducible way to do dimensional analysis and to show other people what you are doing. And that's probably the most important part. Not that you know how to do it, which in and of itself is important, but can you show that to other people and then they know what you did? Because you can't do everything. You're going to be part of a team, presumably, at some point, and you're going to need to show that work to other people. So the first thing that we want to do is I want to take this relationship and turn it into some sort of multiplication, division sort of relationship. A vertical relationship, we'll call it. So what I want to do, and I almost hit Alt-Tab, that's not going to help me there. I'm going to take this relationship, and we're going to do the following to it. So the first thing that I'm going to do is not draw in blue. Let's draw in black here. So I'm going to take this relationship. Uh-oh. Oh, I had a bit of lag there. That's what happened. I'm going to divide both sides by 1 kilogram. And when I do that, I end up on the left side over here with two things that are on one's on top and one's on bottom. In dimensional analysis, anytime you divide by something by itself, the result divides away and it's gone. The outcome of anything divided by itself is always going to be equal to 1. And so what this means is that this term right here equals 1. So I'm going to put it in a box. We're going to come back to it. Michael, to answer your question, remember that these are always posted in the archive, so you can watch them whenever you want to. I don't take attendance, so you don't got to ask my permission. You can do whatever you want. You have agency. What was I doing now? Oh, that's right. I'm going to take the same statement again. And now what I'm going to do is divide by the other side. And 1,000 divided by 1,000 is also 1. Grams over grams is also 1. So, our result that we get here is that this statement is also equal to 1. Now, if something up here equals 1, and something down here equals 1, then the conclusion that we would draw is that they must equal each other. And so in this way, we've proven that taking a vertical relationship like the one indicated at the top can be mathematically turned into the top one's a horizontal relationship. I always get horizontal and vertical mixed up. Taking a horizontal relationship, you can turn it into a vertical relationship. And this is important because I'm going to sneeze, so hold on. As soon as I said that, I didn't need to sneeze anymore, so I apologize. This is important because now what we can use this relationship for is dimensional analysis. We can start multiplying things by either this term on the left here or this term on the right, depending on our need. And we'll show that in more detail in a little bit. Alright. Now, I've called these a unity relationships. I don't know if that term's actually in your textbook. But what's important is that we can turn this top thing, where it's horizontal, into this bottom thing, which is vertical. And we can orient the units on either dimension. We can have a kilogram on top or kilogram on the bottom. We can put it wherever we want to, based on our necessity for the numbers that we're going to convert. For example, if I wanted to figure out how many grams are in 5 kilograms, I could use this relationship here, because this kilogram would then cancel out with this kilogram. If I had it set up the other way, then this unit right here and this unit don't cancel out. And what I get as a result is this. And I don't know what this unit is. Like, that's not something that makes any sense to anybody. However, the units down here, kilograms would get canceled with itself. The only unit that would be left is grams. And that would be my answer. So in dimensional analysis, there will only be one way to create the unit setup such that you get the right answer. And the way to set up the units is such that all the units that you don't want cancel out, leaving only the units that you do. So it's very imperative that you set up your units in this dimension so that they can be canceled out. Now, another way of writing this problem would be to do a sort of like train tracks thing. Since this number is just by itself, I'm going to just put it by itself. And then over here, I have a relationship, and I'm going to write that relationship right here. And then every time I had a unit cancellation, I would just draw another one of these train tracks. This also works. It is all about how you want to set it up. Personally, I just do this sort of thing where I put number after number and I just make it look like a multiplication symbol. But it doesn't matter to me how you set these up, as long as they are showing the dimensional analysis clearly. Yeah, don't tell me you're answering kilograms squared per gram. Like, that doesn't make any sense, right? That's not going to be useful to anybody. Alright, so let's do an example doing some dimensional analysis. A bowling ball weighs 6.8 kilograms. How much does that weigh in grams? It doesn't weigh whatever is on the screen right now, so let's see if I have selected the correct layer. I did, okay. But now I gotta do this to get rid of this thing. And I don't know why it puts this little extra dotted line on my screen here, so get rid of extras. Fortunately, I know how to apparently fix it, so. Alright, so we've got... I gotta look at the other monitor to get the number here. I keep forgetting. So this is our bowling ball, and I want to figure out how much it weighs in grams. I know that I can turn the units of kilograms into grams, and the relationship that I have for that is very simple. 1 kilogram is equal to 1,000 grams. So using this information, I know that I'm going to turn kilograms into grams. So what I'm going to do is I'm going to set up my units so that I involve kilograms and grams somewhere in this calculation. What I want to do is put the unit down here that matches this one so that they go away. So if I put kilograms down here, they would cancel. But, and I don't have a history, so I can't actually undo this all the way. Hold on just a second. I got like 30 little buttons over here, but if I do this, boop, boop, are they not disappearing? Oh, maybe I can't actually edit the history. That's okay. What I can do is this. If I were to do this instead, these units would not cancel, and then I would end up with kilograms squared over grams again, which nobody wants that because that's sad and makes us feel bad. Oops, I zoomed out a little bit. Hold on. Oh no. I didn't even use my... What? Why did that happen? That's okay, it's still on the screen. Okay. So we're going to set up our units like that so that our kilograms cancel. I'm going to turn kilograms into grams here. So that means that on the top here, I got to put that unit. The problem was asking me to convert my answer to grams. I now have an answer that will be in grams. Therefore, I must have all the units set up. So now what I can do is I can run the numbers. So I'm going to plug in the numbers for each of these relationships. How many grams are in a kilogram? In 1 kilogram, there are 10 to the 3 grams. So my answer becomes 6.8 times 10 to the 3 divided by 1, which is just that many grams, or either answer works. So that's a very simple problem. We're going to do much more complex problems as we go through these. All right. Now, if I wanted to figure out how much the bowling ball weighs in milligrams, then there's 2 ways I could go about doing that. So first of all, we got to do this. Oops. So now what we could do is we could take our answer from here, just carry it down, and then we could turn that into milligrams. And we know the relationship between grams and milligrams, so in a milligram, there are 10 to the minus 3 grams. Now, I know that you're going to want to do this conversion. And what I'm going to try and do is encourage you not to do that, because these metric prefixes and the numbers are off of that table. And if you're doing something 2 different ways, that's 2 different ways that you have to memorize all of these problems, and you're going to start reversing things. So I know it's really weird for centi and milli to remember 10 to the minus 2 and 10 to the minus 3, but I'm going to encourage you to do it, just because it will be a lot more beneficial to you to just establish one system in the long term. So once I know my relationship and my path, I can set up the units. I want to cancel out my grams, so I'm going to set it up like this. I'm going to turn that into milligrams. That's the only unit that's left, so those are the units of my answer. That's the units I want, so let's run the numbers. Like we said over here, 1 milligram, 10 to the minus 3 grams. 1 milligram, 10 to the minus 3 grams. And so that gives us the math problem 6,800 times 1 divided by 10 to the minus 3 is going to be 6,800,000, or 6.8 times 10 to the 6 milligrams. Remember that when you are punching numbers into your calculator, use parentheses if you have division. Just because if you have a bunch of divisions in a row and you don't put a parentheses around all of the bottom stuff, then your calculator will divide the first one and then multiply the rest of them and you get a wrong answer. So the general process that I follow to do these problems, and I strongly recommend that you do this, we're going to go like this. 1, 2 for the units, and then 3 for the numbers. So step 1 is to map out your units. Make sure that you know where you are starting and what your target is, and then find a way to get there. Step 2 is to set up all your units. Put all the units down. Don't put numbers down until you have all the units in place. That way you're just thinking about which unit cancels out. So what will this cancel with? Now I have this. What will this cancel with? What will this cancel with? And you just keep doing that. Then finally, for step 3, do the numbers. Then you punch in all the numbers in your calculator and you put all the relationships in, and you're all set. A question was asked, why is it 10 to the negative 3 and not 10 to the positive 3? The reason being is because the relationships between milli and grams is 10 to the minus 3. Remember that the lowercase m is 10 to the minus 3. And we got to have something on both sides of the equation so that that's an inequality. And again, you could have the 1,000 milligrams equals 1 gram, but this number and this lowercase m do not represent the same thing. And that's why I discourage people from using 1,000 milligrams, even though we all know it's true. Mathematically, it's just going to get you mixed up when you're using metric prefixes. I believe the metric prefixes in your textbook are on... Gosh, I don't know what page they're on, actually. I'll have to look at that during the break. I clicked on the wrong screen. There we go. All right. Something very important to note is that if you are doing a problem to go directly from one unit to another, like this, if you want to go through kilograms to milligrams, you cannot do this without doing some mental gymnastics, we'll call it, because there is no relationship on the metric table to relate kilograms and milligrams together. What you always have to do, if you have some unit with a prefix and some unit with another prefix, you have to go through the prefixless unit, okay? So this is known as the base unit, right here. And remember that the base units are things like grams, seconds, meters, liters, moles, that sort of stuff. All right, let's do some more practice problems here. So, for example, this is a statue that I have on my desk. If this was an actual thing, I would estimate that the mass of this orc would be like 150 kilograms, and I want to find his weight in pounds. In your textbook, you have a conversion for pounds to kilograms. And I don't have that on screen, unfortunately. So what I'm going to do is I'm going to do this. And I want to add a window here so that you can see what I'm doing. So let's go to the sample problem preview. That's not a very helpful... It's also really small. Let me see if I can make that bigger. And then what I'm going to do... So I want a window capture. And I didn't make it visible, did I? Oh, that's because it would... Oops, I messed that up. Hold on. Alright, so this... There we go. Let me make this a little bigger. So if you are ever looking for a unit conversion, this is the website that I recommended for you to use from the syllabus. So this is Wolfram Alpha. Wolfram Alpha is basically a calculator. So if I wanted to figure out the conversion between any two units, I could do that and it would tell me that. So now I know that in 1 pound there are 0.4536 kilograms. Now, in the chat, there's another number that was posted, 2.205 pounds per kilogram. You'll notice that that's just the same as doing this and going in the reverse direction. So depending on which direction you put it in, whichever one's your 1, you'll get a different number. So there will always be 2 numbers for these units. You could also just do something like this. And now we don't even have to do the problem at all, because we've just typed it in Wolfram Alpha. On a test, you're obviously going to have to do a little bit more than that. I'm not going to give you something that simple, because I know that this is a thing you could use. However, that is an option for you to use when you're looking up unit conversions. Wolfram Alpha is very reliable. Google probably gets most of the numbers from Wolfram Alpha, so feel free to use either one. I just wanted to show you Wolfram Alpha. If I click on this, or actually if I click on anything, I can show you that the mascot is really creepy. There he is in the top corner. That's actually the least creepy of the mascots that they've had on here. But, yeah, anyway. Boop. Alright, so let's do this problem. So I'll select all, clear, do that. And we are going to figure out the mass of this orc in pounds. Alright, so again, first thing I want to do is set up the units. So I have kilograms as my starting unit. I want to turn this into pounds. And I know that my relationship between kilograms and pounds is equal to 2.205 pounds per kilogram. I think it was 2.205. That's right. Okay. So that was step one. I'm going to set up my unit map, figure out where I'm going, where I'm coming from. Now I'm going to take my starting number, and I want to set up the units such that they cancel. So I'm going to put kilograms on the bottom so it cancels. We'll put pounds on the top. Pounds is the only unit that's left, so pounds is the unit that my answer will be in. That's what I want, so now I can do the numbers. And now I just got to enter in the numbers where I need them. So 1 was with my kilograms, so I'm going to do the same thing over here. 2.205 was with my pounds, so I will do that over here, and it's not getting my decimal points, but that's okay. And so now I just take 150 times 2.205, which you can put in Wolfram Alpha if you'd like. So we could just do it this way. 150 times 2.205. And it spits out 330.75. If you hit enter, it will give you a detailed explanation. It'll even put your answer on a number line if you just love number lines. I don't know. Here it is in fractions. Like, I don't know who programmed this site, but it's wonderful and I love it. And it's also just weird. So, handy to have at your fingertips. Make sure you're using Wolfram Alpha if you've got time. Anyway, the answer that I got was 150 times 2.205, 330 pounds is my answer. Why did I not write 331 instead of 330, though? Why did I stop here? Well, how many sig figs does this answer have? 150 as written has 2 sig figs. This number up here has 4 sig figs. 1 is an exact quantity. Whenever you see 1 in a conversion, you're going to treat it as an exact quantity. In other words, what you're saying is that in exactly 1 kilogram, there are about 2.205 pounds. This is the lowest, so my answer must only get 2 sig figs as well. Everyone's typing in 2 in the chat. That's good. All right, and so there we are. We're all set. All right. On the board, I skipped over all the problems. There we go. On the board, I have a few practice problems for you to do. I'm going to give you 5 or 6 minutes to do these 3 problems. Then we're going to go over the answers. Please bust out your pencil and do these conversions. Use Wolfram Alpha to get the conversion. You can also use Wolfram Alpha to check your answer once you've done it. But what I want you to do is to try and get the answer before consulting the internet for the correct result. Okay? So take a second to do these 3 problems, and I'll be right back to go over the answers. Good luck. We're all counting on you. Alright, just a little bit more and we'll go over the answers. Hopefully you've had enough time to finish these 3 problems. I gotta find my pen. There it is. I'm not good at setting my pen in the same spot every time. Pretty soon it's gonna just roll away. Alright, so let's go over the answers here. I'm holding the wrong button. There we are. Alright, I'm gonna turn pounds into kilograms. So I want my units to be set up like this so that my pounds cancel out. We're going to turn pounds into kilograms like we indicated over here. Kilograms is the only unit that's left. That's the unit that we want. So now we can do the numbers. And I believe the conversion was 2.205. And I need to get a calculator. $579 divided by 2.205. 262.585. But I have a number over here that has 3 sig figs, so my answer should only have 3 sig figs, so it should be 263 kilograms. Problem number 2 is, let's see here. Whoop. I travel 15.5 miles to work each day on my Harley. How far have I traveled in kilometers? The answer is 0 because there's a quarantine. Why are you out on your Harley? Also, I don't really ride my Harley anymore. I bought a Jeep, Jeep Wrangler, and now I don't have to worry about getting wet all the time because I'm driving in a torrential downpour. So I'm going to turn miles into kilometers. There is a conversion for that out there. 15.5 miles, which I will then convert by putting miles down here so it cancels. We're going to turn it into kilometers. Kilometers is the only unit that's left. That will be the unit of my answer. I don't know this conversion off the top of my head, so I got to look it up. So let's see what Wolfram Alpha says. 1 mile to kilometers. I think it's 1.609. Yeah, it is. Okay. 1.609 kilometers per mile. That makes sense because the kilometer is the smaller unit. A motorcycle does provide social distancing because it scares everyone else away. Because it's loud. I also wear a really aggressive-looking helmet. It looks like I'm looking through the eyes of a skull. And apparently that scares a lot of people, and I'm fine with that because I ride a motorcycle. Stay the heck away from me. I don't want to get bumped over. This is the number I got, 24.9 kilometers. That matches with other people got, so that's good. I need to replace that helmet, though. It's very old. Honestly, I need to replace my motorcycle because it's... I put 80,000 miles on it, and I haven't actually touched it for like 8 months, so I don't know how rideable it's going to be. I'm going to take it to the shop. I have leather seats in my Jeep, which seems counterintuitive, I know, for a Jeep, but I don't want to get them wet. Alright, a soda bottle contains 2 liters of soda, so I'm going to turn liters into gallons. My calculator said 24.93, so I would round to 24.9. 25.0 is close enough. I mean, depending on what conversion factor you use, like if you did 1.6093, I don't know if that would affect your answer, but it might. 0.6093. Not enough on mine. I would never wear a kilt during motorcycle riding. Just that sounds like it wouldn't work, I guess. But I do own a kilt, yeah. Let's see here. Liters, gallons. 2 liters. We're going to turn liters into gallons, like so. This one I definitely don't know off the top of my head. It's almost 4 liters per gallon, but I don't remember much. So, liters to gallons. I gotta do it this way. Assuming U.S. liquid gallons, because there are multiple gallons, it turns out. 0.2642 gallons per liter. .2642 times 2. And so my answer that I get here is 0.5284 with 1 sig fig on that 2 liters. That becomes 0.5 gallons. And then finally, I could do liters to microliters and set up the problem like so. Again, liters will cancel. There's my microliters. That's the unit I want. So that must be the unit of my answer. In a microliter, there are 10 to the minus 6 liters. So this becomes 2 times 10 to the 6 microliters. Do you ever need to learn troy ounces in this class? Only if you want to invest in the stock market or buy palladium or something like that. Then it'd be interesting to know that. But I will provide you with all of those numbers. I might ask you a question like, oh, this ball of platinum has 75 troy ounces of material. How many atoms is it or something? That's a chapter 2 question. There's our 4 problems. 3 disguised as 4. We're going to take a 10-minute break, and when we come back, we're going to do more complex dimensional analysis. So more of that after this. I'm going to turn on the title card. We'll put the break time up. I don't have live split open. I got to get that. All right, so that should be a timer. Boop. All right, here we go. See you in 10 minutes. Oh, I got really close to clicking on it on 10 exactly. Maybe at some point I'll do that this quarter. Let's answer some questions. Oops, I turned off the announcements apparently. Hold on. All right. Are going over how to complete the lab worksheets tomorrow. That is the whole point of Wednesday, actually. We're going to do all of the discussion and question and answering stuff about the labs on Wednesdays, because presumably you're going to have at least sort of skimmed over the lab stuff and maybe be like, what the heck is this asking? Or something like that. And the whole point of the lab section is that I'm just going to basically guide you through any questions that you have. I can't tell you the answers outright, but I can at least like direct you where to find them or find the answers. And then I'm going to answer any questions and answers that, or any questions that people might have based on like practice problems or things like that. I actually haven't gotten any questions from students, so if I don't get questions for the Q&A session, then I just like wait 10 minutes, and if nobody has any questions, we call it a day, and then the stream ends early, and that's fine. I mean, we don't have to use all the time. Hopefully everybody read what I posted about due dates for the lab stuff. Currently, there is no due date assigned just yet. That will happen at some point tomorrow. I'm trying to minimize my timer, but I can't. I'll just close it. But other than that, I spent the weekend making those worksheets and the documentation from scratch. So it took a long time. I really hope that it works because I tried to test as many things as I could. I didn't have time to send it to a proofreader because we're all the instructors are basically scrambling. So I read it a few times. I didn't see any mistakes. If there's anything glaring or obvious that's weird, let me know. That's not the screen I want. That's the screen I want. All right. So we're going to finish off Chapter 1 here by talking about some more difficult problems and what you can do to solve them. We have been already using the unit map that allows you to convert from things to one thing to another. Some problems are going to start giving you these, and these are known as conversions. So, what is a conversion? A conversion is a relationship that links two unusual dimensions. For example, I could give you a conversion that tells me how far I move over a given time. That would be something like speed or velocity. I could also give you something that would be a rate, and the rates might be very unusual. For example, maybe I eat 6 pizzas a month. How many pizzas would I eat over the course of my life? You could solve that question. Maybe it's how much medication a person needs per body mass. All sorts of different relationships exist, and it will be very important that we understand how to use them. But the most important thing that you don't want to do is you don't want to start a problem with that. The reason being is that if you start with a conversion, you don't know which way to orient it. You may have to put one of the numbers on top, or maybe you put the other one on the top. You will always have a number that is a constant, and that'll be the number that you start with. You can use that constant dimension to convert to the other dimension and answer the question. The only exception to this is if you were given a problem, and the objective is to turn... I have the wrong color selected. Hold on. So, exception. And the exception is if you have a conversion, and you're going to turn it into another conversion. So, an example of that might be if I turn miles per hour into meters per second. Then you do start with a conversion, and you end with a conversion, because you have to. There is no other option. Alright. And like we've been doing before, we're going to make a little flowchart each time we make a problem, just so we know how to convert stuff to other things. So this first problem is going to be a time problem. How many hours are in 2 years? And this is something that you probably could figure out by multiplying things together. But let's just show all of this worked out on our PowerPoint. Or not our PowerPoint, on the Photoshop document. Boop. I gotta find the problem in here now. Great. There it is. Oops. I'm trying to erase things on Photoshop by clicking on them in OBS, and that's not going to work. Nobody's happy with that. Brush. Okay, I got it. All right. So we got to start with a unit. The first thing that you want to do is you want to use the constant as your starting point. And I only have one starting point. It's 2 years, right? So the units that I will start with are years. Then I'm going to write my endpoint. My endpoint is hours. I want to figure out how many hours are in 2 years. So I need to connect this to this. But I don't have a direct relationship between these two. I have several things that I could do. So for instance, I could turn hours into minutes. Or I could turn hours into days. And then I could turn years into months. But I could also turn years into days. Now you notice that I've put some dead ends on here. And this is because when you're going to be solving these problems, you're not going to necessarily know which connections to make. So writing out all of your possibilities here is a good strategy to figure out, okay, can I link the two target values together? And the answer is yeah. If I go from years to days, and then from days to hours, I can figure this out. I don't need this one, and I don't need this one. So we'll just cross them out. In fact, we can do more than cross them out. We can obliterate them from existing. There we go. That just gives us a little more space. Now I have a relationship between years and days. We can look that up. It turns out it's a little more complicated than you'd think. All right, so I have 2.0 years. And I want to turn years into some unit. So first of all, I got to cancel. So let's do that first. But what do we want to put up here? Well, according to this chart, I'm going to turn years into days. So we'll put days up here. Days is not the unit that I want for my answer because up there it says how many hours are in 2 years. So I got to keep going. I got to do more dimensional analysis. So I'll put another block up. And we'll cancel out days. And now I got to turn it into what the next step on my flowchart is. That's hours. All right. Hours is the unit that I want. So if I do the numbers here, what I will get out is hours. Let's start looking up the relationships here. So how many days are in a year? And everybody is immediately going to go, oh, I know that. It's this. There are 365 days in a year. Of course there are, right? Well, what about leap year? In fact, this year was a leap year. We had February 29th, which was another day you got to stay inside. How do we accommodate for leap year if one of these days, or one of these years that we're counting, happens to be a leap year? Well, it turns out that since a leap year happens every 4 years, we just do this. 1 year is 365 and a quarter days. It's important to know that the way a day is measured relative to a year is not exact. A year is defined as how much time has passed since the planet has elapsed around the sun, or completed an orbit. A day is how many times the planet has rotated in that period. All right. The next one down here, we have days and hours, and we know that there are 24 days in an hour, right? No, be careful. Make sure that you don't accidentally take common numbers and put them in the wrong spot. So in one day, there are 24 hours. That's an exact definition because we have defined one day to be 24 hours, which is why this one up here ends up being inexact. And I almost did the same thing I did down there, except this time on accident, not on purpose. All right, so there's our calculation. We have 2 times 365.25 times 24. And the answer I got was 17,532. But how many sig figs should my answer have? This whole thing is exact because we just said so. 24 hours in a day is a definition. Up here, this number right here has 5 sig figs. This one's exact. But this one right here has 2 sig figs. So therefore, our answer can only have 2 sig figs, which means that I have to round it to 18,000 hours. All right, you've probably noticed that I've been multiplying all my numbers on the top for the most part. That's coincidence. We will be putting numbers on top and bottom based on how our relationships are written out. So don't get used to just putting all the numbers along the top and just timesing everything together. Make sure that you are setting up the problem and doing it in this fashion, and you can't get the answer wrong. All right, let's up the complexity of these problems, and then I'll have you start to... Oops, what did I do? Everything is ruined. Sorry, I hit home, which apparently does this. Yeah, I can just, like, mess up my presentation. That's what I can do. All right. This is how fast I drive. Don't tell the cops. How many minutes will it take me to drive 20 miles? That's significantly more complicated than what we've done so far. So let's try this problem. Now I gotta be careful not to actually draw somewhere you can't see it. Alright, erase. Alright, how low do I... Okay, so this is as far as I can go. Alright, so the first thing that we gotta do is we gotta consider what we're starting with. I have a relationship, which is 75 miles per hour. That would be like me writing this. But it could also be me writing this. I don't know which one of these I'm going to need to use, so I can't start with this conversion. I have to start with the other quantity, which is this quantity. So, knowing that I'm starting there, let's take my miles, and I got to figure out how to turn this into minutes. So do I have anything that I can do with miles? And it turns out, yeah, I can. I can turn miles into hours, right? Because I know how many miles I would cover in an hour. And then turning hours into minutes is very straightforward because in an hour, there are 60 minutes. And so I have that conversion all set up. So let's go and do the problem. 20 miles. Down here, I'm going to put my miles, because I want them to cancel. What am I turning miles into? According to my blueprint that I made, I'm turning them into hours. Hours is not the unit that I want according to the problem. I want to get minutes, so I got to keep doing dimensional analysis. I'll set hours on the bottom to get rid of it. What do I want to turn hours into? We're going to turn it into minutes. So minutes goes here. Minutes is the answer that I want, so when I do this calculation, I will get an answer that is in minutes. So let's do the numbers. I don't know why I keep clicking on this palette changer here. I have 75 miles in an hour, so I got to put 75 with the miles. That actually ends up being down here instead in 1 hour. So we are going to divide in this problem. And then my relationship over here, 1 hour and 60 minutes. Just got to match up the numbers with the units, and I'm all set. So 20 times 60 divided by 75. I got 16 minutes. How many sig figs should my answer have? Well, this is exact, because there are exactly 60 minutes in an hour by definition. This is 3 sig figs, but this is a measured quantity because I am moving a distance in time, so this has 2 sig figs. Therefore, my answer should have 2 sig figs. So 16 minutes is what I want. I accidentally changed to the next problem, which is why you saw a small dog in the window there for a moment. Because the next problem does involve a small dog. This is Scoots. Scoots is a growing puppy, and he needs a lot of food. How much kibble will Scoots eat in 35 weeks if he eats 65.3 grams of kibble every day? So what I want you to try and do, I'm going to give you a few minutes to do this problem. We'll say 5 or so. I want you to tell me how much food you should give this puppy in 35 weeks. And it will be a, disgusting amount of food. Okay, so go ahead and try it. We'll go over the answer in just a bit. I'll see you in a minute. Alright, let's see who starved the puppy and who overfed it. Yeah, we don't want to starve the puppy. It's only going to get worse. The next one is a kitten, so we'll get to that in a second. All these cute animals, and their fate is entirely in your hands. That's adorable, but not terribly useful. Let's see if we can keep Scoots on the board here. Race, guide, and then how far can my cursor go? That far. Okay. Alright, so we gotta feed Scoots. Scoots needs to eat. And we gotta give him the right amount of food. So I know how much food he eats every day, and my goal is to figure out how much he will eat in 35 weeks. So, of those two things, I have this as a value, and then I have this, 65.3 grams per day. And the word per is indicated by the fact that he eats that every day. So I want to start with this quantity, weeks. So that's going to be the start of my grid here, or my little flowchart. And I want to figure out how much he's going to eat in pounds. Now, I don't have a relationship between weeks and pounds, otherwise we'd be done here. I have grams and days, though, so if I could turn this time unit right here into this time unit, I could link them. And then if I could turn this mass unit into this one right here, I could link them. And then finally, I have the relationship between grams and days because it's given right here, 65.3. So we now have a path to get from one end to the other. So let's compute that. So let's start by starting with our number. Start with what you know. And I'm going to turn weeks into days. So I'm going to cancel weeks out. We'll turn it into days. Days is not the number I want. I got to turn days into grams here. So days, grams. This will represent how much food he eats per day. But that will give us an answer in grams. That's not what I want. I want pounds. So I'm going to do grams to pounds. Cancel my grams out. Pounds is the answer that I want, which is what this will give me. So we're all set once we run the numbers. So let's do that. How many days are in a week? Hopefully it's still 7. I don't know. I haven't looked outside for a very long time. How many grams are consumed per day? Up here, that was 65.3 per 1 day. And then finally, how many pounds are in how many grams? I looked that up, but I forgot what the number was, so I have to go get it again. Where's my Wolfram Alpha go? I closed it. I looked it up and I closed it. 1 pound is how many grams? 453.6. That was close to what I thought it was. I could have just looked in chat. I'm sure somebody already mentioned it. There we go. So now I have all those numbers in. I can do the numbers. 35 times 7 times 65.3 divided by 453.6. I got 35.2700 pounds. How many sig figs should my answer have? This is 2. These are exact because we've defined 7 days in a week. This is measured, so it has 3 sig figs. And this is measured, which has 4 sig figs. Therefore, my answer should have 2, which is the smaller of the numbers. So in 35 weeks, he eats 35 pounds of kibble. Since it comes in 40-pound bags, you got to buy a bag every 35 weeks. Just for the puppy. Assuming he doesn't eat more and more as he gets bigger and bigger, and trust me, he will. Alright. This is Maya. Oh, it's not Maya, it's Hazel, sorry. Maya's the name of my cat. Hazel's the name of my old cat, who sadly passed away a few years ago. Don't worry, she was like 22. She was ancient for a cat. But this is a kitten that looked kind of like Hazel. The recommended dose of aspirin for kittens is 3.67 milligrams per kilogram of kitten. How many milligrams should you give to Hazel, who weighs 2.41 pounds? Don't give her too much, or you'll overdose my cat. I'm going to have you guys try this. I'm going to do this, actually, so the problem is on the screen. So I'll give you 5 minutes to try this one, too. And again, please don't overdose my cat. I'll be back to see how you do. Alright, I see we have dosed the cat, but will the cat live? I guess we'll see. The answer is yes, the cat will live, because that's such a tiny amount of aspirin. However, it is a tiny amount of cat, so you never know. Alright, so I know that I can administer this much aspirin per kilogram of cat. Now you're going to notice here that I have two masses. And in order to make sure that we don't get confused by them, this is what I would recommend that you do. This top number is the aspirin. So I'm going to actually indicate that. The bottom number is the amount of cat that we have. And it seems very strange to say how much cat is there. But that's what we're working with, because the other number that we have is this. We have 2.41 pounds. And since that is a mass, I'm going to indicate that it is a massive cat. Mass of cat, not massive cat. And now that's all my information. I'm going to start with the number that's not a conversion, so that's this right here. So let's put that over here to get started in just a second. I put an extra dot. Can I undo? And then we're going to make our little unit map here. So I got pounds of cat. And I want to get to milligrams of medication or aspirin. So I know that if I know the cat's mass in kilograms, I can turn that into milligrams of aspirin. So these are directly already related. I don't know why I wrote that. That's the same thing I just had. I want kilograms of cat. That'll allow me to calculate how many milligrams to give the cat. If I can turn the cat's mass into kilograms, I can solve the problem. So let's do that. So if I turn pounds into kilograms, I'll kilograms of cat, but that's not the answer I want. If I know kilograms of cat, I can then figure out the milligrams medication or aspirin that I will give them. This is the unit that I want. So let's do the numbers. I have a 2.41 pound cat. I forget how many, is it 2.205, I think, pounds per kilogram? I should probably look that up, because by the time that you tell me, it will be like 20 seconds, because internet lag. So, pound to kilogram. $2.205. That's what I read. Okay, cool. And then how much medicine is given to the cat per kilogram? It would be this much, 3.67 milligrams, as we indicated in the problem statement. Punching in all those numbers, I get 2.41 times 3.67 divided by 2.205. 4.01 milligrams of medicine for the cat. We did not overdose the cat. The cat will be happy and healthy. And do we have the right number of sig figs? This has 3. This is 4. This has 3. Our answer has 3. Alright, so that was Maya the... Or not Maya the cat. That was Hazel the cat. We're going to do this. And then we're going to do this. So you can just see the loving eyes of the cat that you've saved. Oh no, don't overdose the cat. That would be bad. Alright. Here's some more problems for you to try. I was apparently playing Dragon Quest, I think this is 11, when I was doing these problems. So these are more complex problems. I'm going to let you try these, and we're going to go over them at the very end of class. I'll give you about 6 or 7 minutes to do all 3 of them. Being off by 0.01 is totally fine. What I would not accept is being off by like 0.7, or like being off by more than that. Like, that's just too much. If you're within like plus or minus 1 or 2 on the last digit, that's fine. Alright, so here are 3 questions for you to do. How long in minutes would it take to travel 36.5 miles at a speed of 81.3 kilometers an hour? If I pay $10 a pound for salt, how much would I pay for 15 kilograms of it? And then here's a troll. It weighs 825 pounds. How much does he weigh in milligrams? And how many hits will it take Monty to kill him? The answer is 1 to that one, because Monty is a powerhouse, and your main character in Dragon Quest XI is utterly broken. Alright, so go ahead and solve those problems. If I do this, it's probably going to have a giant troll, so I got to fix that. I don't know if I can fix that now. I've scrolled the usable space off the screen, so I'll work on that. So write down the problem, and I'll be right back. . Just a minute or so to finish it up. I actually have a stopwatch here that I watch, so I give you guys enough time, because otherwise I'll be like 30 seconds, and then I'll be like, okay, that was enough time, because I'm bored or something. But I see a bunch of answers, and that's great. We're going to go over the answers in just a second. Let me actually set up the problem card here. Because we don't actually... Uh-oh, what did I do? I'm selecting multiple things. What am I moving? Oh, I'm moving a window capture, which doesn't exist anymore, so I can just remove this. Oh, no, I don't want to do that. Just want to remove this one. There you go. So, select all, delete, guide, pen. Okay. Let's go over the answers. So this first one, I'm going to skip the part where I write out the blueprints, because we're a little short on time, and I just want to go over the answers here. So I will just write out the solutions. So 36.5 miles. I'm going to turn miles into kilometers. And then I will turn kilometers into hours, so that miles cancel out. Kilometers cancel out. That gives me hours. Looks like I want minutes for my problem, so I will do that. This should give me an answer in minutes. If I am going, let's see here. I don't remember how many kilometers are in a mile. It's like 1.6 something. I still have Wolfram Alpha open though. So 1 mile, 2 kilometers. 1.6093. 1.6093. That's good enough. How many kilometers per hour am I going? I am going 81.3. And then in an hour, there are 60 minutes. So punching this all into my calculator. I got 43.4 minutes. Actually, I got 43.3. I can't make that into a 3. There we go. That's what everyone else seemed to get, so that's good. If salt costs $10 a pound, how much would I pay for 15 kilograms? This is the number that is not the conversion. I got to get that into some sort of pounds, so I'm going to do kilograms. Turns into pounds. And then I'll turn pounds into money. I think that that's right, 1.2 or 2.204 per pound. Or pounds per kilogram. And then it cost me $10 per pound of salt. Let me just look that up real quick. So 1 kg, 2 pounds. Yeah, that's right. Okay. Could be 2.205. That's close enough. Calculator says 15, 2.204. It's going to cost me $331 to buy all this salt. I actually think $10 per pound of salt is probably rather expensive, considering how much salt we consume and how cheap it is. And then finally, I clicked off the screen. There you go. Finally, I have an 825-pound patrol. We want to turn that into milligrams, so we'll do pounds per... That's not what I want. Thinking and talking at the same time is difficult. There we go. We'll turn pounds into kilograms. I don't know how people are hoarding so much food. I live alone, and I'm trying to buy 2 weeks of food at a time. And I can't. My food goes bad before I eat all the food. Kilograms to grams. Grams to milligrams. Alright, I literally just did this, so this should still be the same number. 1 kilogram is 1,000, or 10 to the 3 grams, and 1 milligram is 10 to the minus 3 grams. These don't cancel, they're not the same number, so be careful. 825. And I need scientific notation for that. Oops, that's not what I want. Oh, calculator, why are you being obnoxious? There we go. 3.74 times 10 to the 8 milligrams. I could have just looked at the chat. If I see the same number 8 times, the odds are you all did it right. Alright. Those are the types of problems that we're going to be doing in this class. We're going to be calculating the weight of trolls and orcs all the time. No, not really. But what we are going to be doing is this style of calculation. We're going to be converting from grams to moles, liters to milliliters to moles to all sorts of things. I don't think that there are any other slides left in Chapter 1. Is that it? Oh, temperature scales. Yeah, I don't really care about temperature very much. Is this all I have left? I don't know. We'll start here on Thursday. We'll definitely finish Chapter 1 on Thursday, but bring your slides for Chapter 2. 374 times 10 to the 6 is the same number. That's not correct in scientific notation, but it is correct in engineering notation. Engineering notation is just, hey, I'm only going to allow powers of 10 to be multiples of 3. I don't know why that's a thing, personally, but it is a thing that exists. So I accept either answer. I'm pretty sure that if you typed that into Canvas, it would move the decimal and be fine with it. But yeah. Anyway, I want to thank everybody for coming to lecture today. I hope that you learned something about dimensional analysis. This is the sort of technique that we're going to be doing a lot throughout the quarter. On Thursday, we're going to be doing Chapter 2. We'll also finish Chapter 1 by talking about temperature just very briefly. Tomorrow for Wednesday, between now and then, I want you to have at least downloaded the PDF for the lab assignment, and also downloaded a copy of the Google Sheet to your own Google Drive, and be able to access that and type in numbers, because during the period, I'm going to let you just work on the stuff. I'm going to hang out for a bit. I might not have the video streaming, but if you send me questions through the chat, I will still be able to answer them. We'll just kind of play it by ear tomorrow and see how that goes. A general overview will also be provided. It is the same time as the lectures are normally, so 1 to 3. I do not expect it will go till 3. I think, like, if we start at 1, it'll probably take me 30 minutes to explain how to do the lab and get all the files and do whatever. And then it's very straightforward. I think the only questions that will probably come up will be things like, how do I make a chart in Google Sheets? And I tried to explain that a little bit, but I can show you how to make a chart. It's actually really easy. Things like that. So read through it. If you have questions, have them ready. We can go over them at the start of the period. If there aren't any other questions, I'm going to leave the chat open for a little bit. I'm just going to put the title card on the screen. Thanks for watching. I'll see you all tomorrow for the lab lecture.